Welcome to this coding walkthrough. Today, we'll be tackling an interesting problem titled Closest Room from LeetCode, problem number 1847. This problem challenges us to find the closest room based on a set of queries, testing both our algorithmic thinking and optimization skills. Let's dive in. In this problem, we are tasked with finding the most suitable room for a series of queries based on two conditions. You are given an array of rooms, where each room is represented by a unique room ID and a size. The array rooms, I, equals, room underscore ID underscore I, size underscore I, tells us that the room with ID room underscore ID underscore I has a size of size underscore I. Along with this, you are also given a set of queries. Each query consists of two values, a preferred room ID and a minimum size requirement. For each query, we need to identify a room that satisfies two conditions. First, the room's size must be greater than or equal to the minimum size specified in the query. Second, the room's ID should have the smallest absolute difference from the preferred ID in the query. If there are multiple rooms with the same absolute difference in their IDs, we should select the room with the smallest room ID among them. If no room meets the criteria for a query, the result for that query will be -1. Finally, we return an array of results, where each element corresponds to the answer for a specific query. Let's go through an example to understand the problem better. Suppose the input rooms array is 2, 3, 1, 5, 3, 8, and the queries array is 2, 4, 3, 7, 1, 5. The output for this example is 1, 3, 1. Here's why. For the first query, 2, 4, we are looking for rooms with a size of at least 4. The valid rooms are 1, 5, and 3, 8. Among these, the absolute difference between their IDs and the preferred ID, 2, is 1 for both rooms. Since the room with the smallest ID between them is 1, 5, the answer is 1. For the second query, 3, 7, the only room that meets the size requirement of 7 is 3, 8. The absolute difference between its ID and the preferred ID, 3, is 0. So, the answer is 3. Finally, for the third query, 1, 5, the only room that meets the size requirement of 5 is 1, 5, and its ID matches the preferred ID, making the answer 1. Now, let's consider another example to explore additional scenarios. This time, the rooms array is 2, 2, 1, 2, 3, 2, and the queries array is 3, 1, 3, 3, 5, 2. The output for this example is 3, -1, -1. For the first query, 3, 1, all rooms have a size greater than or equal to 1. The room IDs available are 1, 2, 3. Among these, the room with the smallest absolute difference from the preferred ID, 3, is 3, 2, so the answer is 3. For the second query, 3, 3, none of the rooms have a size greater than or equal to 3, so the answer is -1. For the third query, 5, 2, all rooms again meet the size requirement of 2, and the room IDs are 1, 2, 3. However, there is no valid room with an Idaho close enough to the preferred ID of 5, so the answer is -1. To solve this problem efficiently, we need to account for the constraints, which allow up to 100,000 rooms and 10,000 queries. First, we can sort the rooms array by size in ascending order and sort the queries array by their min_size requirements. Then, we can use a sliding window or a data structure like a tree set in Java or a sorted list in Python to maintain a dynamic list of room IDs that meet the size condition as we process each query. For each query, we calculate the absolute difference between the preferred ID and the room IDs in our list. Using binary search, we can efficiently determine the room with the smallest difference. If there are ties, we select the room with the smallest ID. This approach ensures that we handle edge cases, such as no rooms meeting the size constraint, multiple rooms having the same absolute difference, and scenarios with large input sizes, within the given time complexity limits. To start, let's consider the brute force approach. The basic intuition here is to process each query by iterating through all the rooms to find the closest one that meets the size requirement. For each query, we first filter the rooms to include only those with a size greater than or equal to the query's minimum size. Then, among the filtered rooms, we determine the one with the smallest absolute difference in ID relative to the preferred room ID specified in the query. While this method is straightforward and simple to implement, it's computationally expensive. Filtering rooms takes n time for each query, and with m queries, the total time complexity ends up being m*n. This makes the brute force approach infeasible for larger inputs, where both n and m can go up to 10,000. The trade-off here is that while it's easy to implement, it lacks scalability and performs poorly on large datasets due to its inefficiency. Now, to address the inefficiencies in the brute force method, we can optimize the solution using sorting combined with binary search. Instead of filtering the rooms individually for each query, we pre-process the rooms and queries upfront to reduce redundant operations. First, we sort the rooms by their sizes in descending order, and we do the same for the queries based on their minimum size requirement. Then, as we process each query, we maintain a dynamic set of valid room IDs, for example, using a sorted data structure like a tree set in Java or a sorted list in Python. As we iterate through the queries, we add rooms to the set only when their size meets the current query's requirements. Finally, to find the closest room, we use binary search on the sorted room IDs. This approach leverages the pre-sorting step to ensure that we only work with valid rooms, while binary search minimizes the cost of finding the closest room. In terms of complexity, sorting the rooms in queries each takes n*log n and m*log m, respectively. Adding rooms dynamically is n, and binary searching within the valid room IDs is log n. Overall, the total complexity is n plus m*log n, which is a significant improvement over the brute force solution. The trade-offs in this optimized binary search approach make it well-suited for large datasets. It's efficient and relatively straightforward to implement, but it does require careful handling of sorted data structures and binary search. Alternatively, we can consider another optimization using segment trees or range query data structures. In this approach, we pre-process the rooms into a segment tree where room IDs are keys and their sizes are values. For each query, we use the segment tree to perform range queries to dynamically find the closest valid room. The complexity here is similar to the binary search method. Building the segment tree takes n*log n, and performing range queries for m queries takes m*log n, resulting in an overall complexity of n plus m*log n. However, while segment trees offer comparable efficiency, they introduce additional complexity in terms of implementation and debugging, making them less practical for this specific problem. Given the options, the chosen strategy for this problem is the optimized approach using sorting and binary search. This method strikes a balance between simplicity and efficiency, making it a practical choice for handling the problem constraints. By pre-sorting the rooms and queries, we eliminate redundant computations and ensure that we only add valid rooms dynamically as needed. Sorting the queries also allows us to process them in a way that minimizes unnecessary work. Additionally, using a sorted data structure for room IDs enables efficient binary search to find the closest room. Compared to the brute force approach, this method is vastly more efficient, and while segment trees offer similar performance, they introduce unnecessary complexity. Overall, sorting and binary search emerge as the preferred solution due to their ease of implementation and scalability for larger datasets. Despite its advantages, the optimized sorting and binary search approach does come with some trade-offs. For instance, the pre-processing step adds slightly higher overhead due to the need to sort both rooms and queries. Additionally, edge cases, such as queries for which no valid rooms exist, require careful handling to ensure the solution remains robust. Nevertheless, these challenges are manageable, and the approach remains both efficient and practical within the problem constraints. By balancing pre-processing costs with efficient query handling, this strategy provides a scalable solution that performs well even for the largest permissible input sizes in this problem. To tackle the problem of finding the closest room for a set of user queries, we start by understanding the requirements. Each room is defined by an ID and a size, and each query specifies a preferred room ID along with a minimum size requirement. A room is valid for a query if its size meets or exceeds this minimum size. Among all valid rooms, we need to find the one with the smallest absolute difference between its ID and the preferred ID. If there's a tie in the absolute difference, the room with the smaller ID is chosen. If no room meets the query's requirements, we simply return -1. To approach this, the first step is to organize the inputs. We extract the rooms array, where each room is represented as a pair of room_ID size. Similarly, we extract the queries array, where each query is formatted as preferred_ID, min_size. Additionally, we assign an index to each query to preserve the original order of results after processing. At the end of this step, we have a list of queries with their original indices, which we'll refer to as queries_with_index. Now that we have the inputs organized, the next step is to sort the data for efficient processing. First, we sort the rooms array by size in descending order. This allows us to add rooms to our candidate set iteratively, ensuring that every room we consider will meet the size requirement of the current query. Next, we sort the queries_with_index array by min_size in descending order. This ensures that we handle the largest size constraints first, which aligns with the descending order of room sizes. These sorted structures, which we'll call rooms_sorted and queries_sorted, help streamline the process. To efficiently find the closest room for each query, we use a balanced data structure, such as a sorted set from Python's sorted containers library. This structure allows us to dynamically maintain the set of room IDs while enabling fast binary search operations. For each query in queries_sorted, we iteratively add all rooms from rooms_sorted that meet the current query's min_size requirement into the sorted set. Once the valid room IDs are added, we perform two binary searches, one to find the closest ID greater than or equal to the preferred ID, and another to find the closest ID less than or equal to it. By comparing the distances from these two candidates, we select the closest room. If no valid room exists, we return -1 for that query. After processing all queries, we need to ensure that the results are returned in the correct order, matching the original input order of the queries. To achieve this, we use the indices stored in queries_with_index to map each result back to its corresponding query. Once all results are stored, we return them as a list of closest room IDs, or -1 for queries where no valid room exists. Several key insights make this approach efficient. First, sorting both rooms and queries reduces redundant checks by ensuring that we process each room and query just once. Second, the balanced data structure, such as a sorted set, provides fast insertion of room IDs and efficient binary search operations, both of which are critical for performance. Finally, binary search itself allows us to quickly locate the closest valid room ID, avoiding the need to iterate over all room IDs. In terms of data structures, we rely on a sorted list for maintaining room IDs dynamically, a list of tuples for storing and sorting queries with their indices, and a results array to store the final output in the correct order. To understand the efficiency of this approach, let's analyze its complexity. Sorting the rooms array takes r*log, r, where r is the number of rooms. Similarly, sorting the queries array takes q*log, q, where q is the number of queries. Processing each query involves potentially adding up to or rooms to the sorted set, which takes r*log, r, and performing two binary searches on the sorted set, which takes log, r, per query. In the worst case, the total time complexity is r*log, r, plus q*log, q, plus q*r*log, r. Several edge cases must also be handled carefully. If no rooms satisfy the size constraint for a query, we return -1. When all rooms are valid, we ensure that the closest room is chosen based on the rules for absolute difference and smaller ID. Finally, in case of ties where two rooms have the same absolute difference, we must choose the room with the smaller ID to meet the problem's requirements. By addressing these edge cases and leveraging efficient data structures, this solution ensures correctness and scalability for the problem. Here, we start by importing the bisect module, which will help us efficiently perform binary search operations later in the solution. The problem involves finding the closest room for each query, and we begin by defining a method closest room within the solution class. First, we pair each query with its index to maintain the original order of the queries, since we'll be sorting them later. This is achieved by creating a new list called indexed_queries, where each element is a tuple containing the query's minimum room size, preferred room ID, and its original index. Next, we sort these queries in descending order based on their minimum room size requirement. This ensures that we process the most restrictive queries first. Similarly, we sort the list of rooms by their sizes in descending order so that we can easily pick the largest rooms that meet the minimum size requirement. After sorting, we initialize two key variables, results, an array to store the results for each query, and valid_room_IDs, which will hold the room IDs of eligible rooms that satisfy the size constraint. We also define a room_index variable to keep track of our position in the sorted rooms list. For each query in indexed_queries, we iteratively add rooms that meet the query's minimum size to the valid_room_IDs list. Once we've added all such rooms, we sort the valid_room_IDs list to enable efficient binary search for the closest room ID. If there are no valid rooms, we set the result for the current query to -1, indicating that no suitable room was found. If there are valid rooms, we use binary search to locate the closest room ID to the preferred ID of the query. This is done using the bisect_left function from the bisect module, which returns the index where the preferred ID would fit in the sorted valid_room_IDs list. We then initialize a variable closest to infinity to keep track of the closest room ID found so far. If the position returned by bisect_left is within the bounds of the list, we first check the room ID at that position and update closest if it's a valid candidate. Additionally, if the position is greater than 0, we also consider the room ID just before this position. By comparing the absolute differences between these candidates and the preferred ID, we ensure that the closest room is selected. Once the closest room ID is determined, we store it in the results array at the appropriate index corresponding to the original query order. After processing all the queries, the method returns the results array, which contains the closest room ID for each query. This approach ensures efficiency through sorting and binary search, making it well-suited for the problem's constraints. Here, we begin by defining the Java implementation of the closest room method. The goal is to process a series of queries to find the closest room based on specific conditions. First, we initialize an array called indexed queries to keep track of the original indices of the queries. This is important because the results need to be returned in the same order as the input queries. Each query is transformed into a triplet where the first value is the minimum required room size, the second value is the preferred room ID, and the third value is the original index of the query. Next, we sort the indexed queries array in descending order of the minimum room size, ensuring that we address queries requiring larger rooms first. Similarly, we sort the rooms array in descending order of their sizes. This allows us to efficiently match rooms to queries as we iterate through them. We then initialize an array called results to store the final answers in a tree set called valid room IDs. The tree set will help us maintain eligible room IDs in sorted order, enabling quick lookups for room IDs that are closest to the preferred ID. Finally, we set up a variable room index to track our position in the rooms array as we iterate through the queries. Now, we start processing each query from the indexed queries array. For each query, we extract the minimum required room size, the preferred room ID, and the original query index. Using a while loop, we add all rooms with sizes greater than or equal to the current query's minimum size to the valid room ID set. This ensures that only eligible rooms are considered for the current query. Once no more rooms meet the size requirement, we proceed to find the closest room ID. If the valid room IDs set is empty, it means no eligible rooms exist for this query, so we set the result to -1. Otherwise, we use the treeset method's floor and ceiling to find the closest smaller or equal room ID and the closest larger or equal room ID, respectively, relative to the preferred ID. Depending on which of these values is closer to the preferred ID, we assign the result for this query. If both values exist, we compare their distances to the preferred ID. If only one of them exists, that becomes the result. This process ensures that we always select the closest valid room ID according to the query's requirements. Finally, after processing all the queries, we return the results array, which contains the closest room IDs for each query in the same order as the input. The implementation wraps up here, ensuring that all edge cases, such as no valid rooms or ties between two room IDs, are handled correctly. This approach efficiently uses sorting and the treeset data structure to provide an optimal solution to the problem, balancing clarity and performance. We begin with the first example, where the input consists of rooms 2, 3, 1, 5, 3, 8, and queries 3, 5, 3, 2. The first step is to pre-process the queries by adding their indices to maintain the original order. This gives us indexed_queries equals 5, 3, 0, 2, 3, 1. Next, we sort these queries by their minimum room size in descending order. In this case, the queries are already sorted, so the order remains 5, 3, 0, 2, 3, 1. Then, we sort the rooms by their sizes in descending order, resulting in 3, 8, 1, 5, 2, 3. After this, we initialize an array results equals 0, 0 to store the answers for each query and an empty list valid_room_IDs to keep track of valid room IDs as we process the queries. For the first query, min_size equals 5, preferred_ID equals 3, we add all rooms with a size greater than or equal to 5 to valid_room_IDs. This means adding rooms 3, 8, and 1, 5, so valid_room_IDs equals 3, 1. We then sort this list to get valid_room_IDs equals 1, 3. Using binary search, we locate the position of the preferred room ID, 3, which is at index 1. The closest room is 3, so we update results, 0 equals 3. For the second query, min_size equals 2, preferred_ID equals 3, we add rooms with a size greater than or equal to 2. This includes room 2, 3, making valid_room_IDs equals 1, 3, 2. Sorting gives valid_room_IDs equals 1, 2, 3. Performing a binary search for the preferred room ID, 3, we find its position at index 2. The closest room is 3, so we update results, 1 equals 3. Finally, the output for this example is results equals 3, 3. In the second example, the input consists of rooms 5, 10, 6, 15, 7, 20, and queries 10, 6, 15, 7, 5, 5. First, we preprocess the queries by adding their indices, resulting in indexed_queries equals 6, 10, 0, 7, 15, 1, 5, 5, 2. We then sort these queries by their minimum size in descending order, resulting in 7, 15, 1, 6, 10, 0, 5, 5, 2. Next, we sort the rooms by their sizes in descending order, giving us 7, 20, 6, 15, 5, 10. We initialize an array results equals 0, 0, 0 to store the answers and an empty list valid_room_IDs to track valid room IDs as we evaluate each query. For the first query, min_size equals 7, preferred_ID equals 15, we add all rooms with a size greater than or equal to 7 to valid_room_IDs. This means adding room 7, 20, so valid_room_IDs equals 7. Since there's only one ID, sorting isn't needed. Performing a binary search, we find the closest room is 7, so we update results, 1 equals 7. For the second query, min_size equals 6, preferred_ID equals 10, we add rooms with a size greater than or equal to 6. Adding room 6, 15 results in valid_room_IDs equals 7, 6. Sorting gives valid_room_IDs equals 6, 7. Using binary search, the closest room is 6, so we update results, 0 equals 6. For the third query, min_size equals 5, preferred_ID equals 5, we include rooms with a size greater than or equal to 5. Adding room 5, 10 updates valid_room_IDs equals 6, 7, 5. After sorting, we have valid_room_IDs equals 5, 6, 7. The closest room is 5, so we update results, 2 equals 5. The output for this example is results equals 6, 7, 5. In the third example, we have rooms 4, 2, 8, 6, 3, 1, and queries 6, 3, 2, 4. Pre-processing the queries by adding their indices gives indexed_queries equals 3, 6, 0, 4, 2, 1. After sorting these queries by their minimum size, we get 4, 2, 1, 3, 6, 0. Then, we sort the rooms by their sizes in descending order, resulting in 8, 6, 4, 2, 3, 1. We initialize results equals 0, 0 to store the answers for each query and an empty list valid_room_IDs to track valid room IDs during processing. For the first query, min_size equals 4, preferred_ID equals 2, we add all rooms with a size greater than or equal to 4 to valid_room_IDs. This includes rooms 8, 6, and 4, 2, resulting in valid_room_IDs equals 8, 4. Sorting gives valid_room_IDs equals 4, 8. Using binary search, we find the closest room is 4, so we update results, 1 equals 4. For the second query, min_size equals 3, preferred_id equals 6, we add rooms with a size greater than or equal to 3. Adding room, 3, 1, results in valid_room_ids equals 4, 8, 3. Sorting gives valid_room_ids equals 3, 4, 8. The closest room is 8, so we update results, 0 equals 8. The output for this example is results equals 8, 4. To analyze the time complexity of the solution, we start by breaking down the major steps. First, we have the sorting operations. Sorting the rooms array by size in descending order takes O(m*log m, where m represents the total number of rooms. Similarly, sorting the queries array by their min_size values in descending order requires O(n*log n, where n is the number of queries. These sorting steps are foundational as they prepare the data for efficient processing. Next, during query processing, we iterate through the rooms array to add rooms that meet the min_size condition for each query. Across all queries, this step examines each room at most once, contributing O(m) to the overall complexity. Additionally, after adding rooms to the valid_room_ids list, we sort this list. In the worst-case scenario, up to m room IDs may need to be sorted for each query, leading to a complexity of O(n*m*log m for this operation. Finally, for each query, we perform a binary search on the valid_room_ids list to find the closest room ID. Since binary search on a sorted list takes O(log m), this step contributes O(n*log m) across all queries. These components together shape the time complexity of the solution. Now, when combining all the steps discussed earlier, the dominant term in the solution is the sorting of the valid_room_ids for each query. This operation, which occurs n times and involves sorting up to m elements, has a time complexity of O(n*m*log m. Therefore, the overall time complexity of the solution is O(n*m*log m. Moving on to space complexity, the storage required for the rooms and queries arrays is O, m, and O, n, respectively, as they are part of the input. Additionally, we create an augmented version of the queries array, referred to as indexed_queries, which also requires O, n, space. The valid_room_ids list, used to store up to m room IDs during query processing, contributes another O, m, to the space usage. Finally, the results array, which stores the output for each of the n-queries, has a size of O, n. These components together define the space requirements of the solution. For auxiliary space usage, the sorting operations on the rooms and queries arrays require O(log m and O(log n) space, respectively. However, these are negligible compared to the other space terms. Thus, the dominant space term is O(m), contributed by the valid_room_ids list, which can store all room IDs. Combining this with the space for queries, the overall space complexity becomes O(m plus n). To understand the efficiency of the solution, let's compare it to a brute force approach. In a naive solution, we would check every room against every query, resulting in a time complexity of O(n*m). While this method avoids sorting, it performs significantly more redundant checks, making it inefficient for large datasets. The optimized solution, on the other hand, leverages sorting and binary search to minimize unnecessary operations. By filtering and searching efficiently, it improves the time complexity to O(n*m*log m, which is far more scalable. Analyzing the best, average, and worst-case scenarios further illustrates the behavior of the solution. In the best case, all queries have min_size values smaller than the size of the smallest room. Here, the valid_room_ids list remains empty, avoiding sorting and binary search altogether. The time complexity is then dominated by the sorting of rooms and queries, resulting in O(m*log m plus n*log n. In the average case, typical inputs lead to a proportional growth of valid_room_ids with m. As a result, the time complexity balances out at O(n*m*log m. Finally, in the worst case, all queries filter nearly all rooms, causing the valid_room_ids list to grow to size m for every query. Sorting and binary searching this list for each query results in the same O, n asterisk m asterisk log, m, time complexity. To validate this, we rely on mathematical principles. Sorting a list of size k takes O, k asterisk log, k, while binary search operates in O, log, k. When these operations are combined across n queries in m rooms, the derived complexity of O, n asterisk m asterisk log, m, is confirmed to hold true. Here, we address some common mistakes that can arise when solving the closest room problem. First, one recurring issue is misunderstanding the constraints. This might include failing to handle edge cases, such as when there are no valid rooms for a query or when the input is empty. In these situations, your solution should explicitly account for such cases, for example, by returning -1 if no room meets the size constraint. Next, inefficient search implementations can be a major pitfall. Approaches like nested loops, which result in O, q asterisk n, time complexity, become infeasible as the input size grows. Instead, optimizing with techniques like binary search or balanced trees can significantly reduce complexity. Another mistake involves sorting. If you sort the rooms or queries but don't track their original indices, your results may not align correctly with the queries. A simple fix is to store their original indices during sorting. Finally, overlooking the requirement to return the smallest room ID in case of ties can lead to wrong outputs. When two rooms satisfy a query, the solution must ensure the room with the smaller ID is chosen, as this is often explicitly required in the problem description. Another common issue is poor handling of duplicates. For example, if room sizes or IDs are not unique, failing to account for this can result in incorrect outputs. Always check the problem's constraints carefully to determine how duplicates should be managed. Shifting to interview-specific insights, many problems like this one involve constraints like finding the closest or smallest. In such cases, sorting combined with binary search or even two-pointer techniques tends to be the optimal solution. Pattern recognition is also key. Problems in this category often involve pre-processing the input for efficiency, such as sorting rooms, and then using a structure to query results quickly. This pattern frequently appears in interval or range-based problems. To optimize, focus on pre-processing data so each query can be answered in logarithmic or near constant time. Consider advanced data structures like a tree set or Fenwick tree for efficient range queries. Finally, during interviews, always clarify ambiguous constraints, such as how to handle ties or special edge cases. This not only ensures your solution is correct but also demonstrates your attention to detail. Now, let's explore some related problems that can help build intuition for this type of challenge. For example, LeetCode 410, split array largest sum, involves partitioning arrays efficiently, which shares conceptual similarities in optimizing constraints. Another problem, LeetCode 977, squares of a sorted array, applies sorting and two-pointer techniques, reinforcing useful tools for range-based queries. LeetCode 658, find k closest elements, is another great example that uses binary search to locate values closest to a target. Finally, LeetCode 315, count of smaller numbers after self, highlights the use of binary search trees or Fenwick trees to perform efficient range queries. Each of these problems introduces patterns or techniques that are highly transferable to the closest room problem, so solving them can deepen your understanding and improve your problem-solving skills. Finally, let's compare some alternative approaches and their trade-offs. A brute force solution, with time complexity O, q asterisk n, is straightforward to implement but becomes impractical for large inputs. This approach, however, can be useful for validating more optimized solutions. A more efficient method involves sorting the rooms by size and using binary search to find the closest valid room for each query. While this has a time complexity of O, n plus q, asterisk log n, and reduces query time significantly, it introduces pre-processing overhead. For dynamic updates, a tree set or balanced binary search tree can maintain a dynamic set of valid rooms, making range queries efficient with the same time complexity. However, this comes at the cost of increased implementation complexity. Lastly, the two-pointer technique offers a highly efficient O, n plus q, solution under specific conditions, such as when both rooms and queries are sorted. While it's optimal for certain scenarios, its applicability depends on the input being pre-sorted. Each approach has strengths and weaknesses, so the choice depends on the constraints and requirements of the problem at hand. Great job! We've successfully completed the closest room problem. Today, we learned how sorting and binary search can simplify complex queries. Remember to practice similar problems to strengthen your understanding. Thanks again for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!